To blur an image, you can use a convolution matrix, but what values should be in that matrix? Well, Pascal's triangle can help us out with that. Pascal's triangle is defined at its core by a simple recursive function that says, given any column and row, if it's the first column or the first row or the last column, its value is always 1, otherwise its value is a combination of the column to the left and the row above and the same column in the row above. That produces this output. We can see also the number of values in a row is defined by the row plus 1. So we can see row 0, it's got 1 value, that's positional value, column 0, row 0. So we can have a look and say, does that satisfy this condition? Yes, it does. So its value is 1. In row 1, we can see it's got 2 values. That's the first column, so its value is 1. That is not the first column and not the first row, but it is the last column, so its value is also 1. Then when you get into row 2, it becomes recursive. So we've got 1 because that's the first column. We've got 2 because that's a combination of the same column in the row above plus the column to the left in the row above, which is 1 plus 1, which gives us 2. And then our last value in row 2 is 1 because that's the last column. And we can see that is how all these values have been produced. We can also see that the number of calls made to produce the values in any row quickly escalates. Approximately it's 2 to the row plus 1, but we can define it by saying it's 1 for row 0, it's 2 for row 1, and it's 2 times the number of calls you needed to make for the previous row plus the previous row otherwise. So if you wanted, for instance, 33 values, you would use row 32, and you can see you'd need 8,589,934,559 calls to produce your 33 values. This is obviously not good enough, so we need a non-recursive version to produce the values. The non-recursive core Pascal triangle function is exactly the same, apart from we pass in the row above, so it's not recursive and it simplifies things. So what we do is we take advantage of the fact that you only ever need, if for instance you're looking for row 9, you only ever need 9 divided by 2 plus 1 columns. So 9 divided by 2 is 4, plus 1 is 5. You only ever need 1, 2, 3, 4, 5 columns at maximum when you're producing the values for any row. 5 obviously for some rows is beyond the number of values in that row, but for some rows it's not, so that's an optimization. We would not bother producing these values. So what you do is, if you want row 9, you go from row 0, calculating all the values, bearing in mind our mid-column optimization, all the way down to row 8, and then when you've got those values, for instance for row 9, when you've got those 5 values, you would then pass those in to this function, and it would produce half the values you need for row 9. Half the values is not what we're after. We want all the values, so to finish off the production of any row, you mirror the values that you've created, that you've calculated, and then populate the rest of the array with the mirrored values, and that gives you all the values you need for any given row. So how much of an optimization is this? Well, it's a large optimization. You say for any row, you take that number, you minus half plus 1, our midpoint optimization, and you multiply it by half plus 1, and you also include the sum, the inclusive sum of 1, to the row number divided by 2. So for our row 32 that we require 33 values from, we can see that the number of calls made to our non-recursive function is 425. So 425 functions as opposed to 8,589,934,559, which is a very good optimization. So now we can use our non-recursive implementation to get the values for any row in a Pascal's triangle. So how does that help us? Well, if we want a 33 by 33 convolution matrix, we can use our non-recursive implementation to get row 32, 0 base 32, which will give us our 33 elements. These are those 33 elements. The last half again are just mirrored, and the total, the sum of that matrix would be 4,294,967,296. So we have a row 32 set of values, and we have a matrix of 33 by 33 elements, which we can now populate by saying, given the row that we've calculated, if you want to populate column C and row R in M, you would say the previous values will take C and we'll multiply that by the previous values and we'll take R, and that would enable us to populate completely our 33 by 33 convolution matrix. The sum of that would be the sum of the row multiplied by the sum of the row, which could then be used to normalize our convolution matrix, which we would divide throughout by that sum, and the sum of our convolution matrix would now then be 1. And we could then use that matrix to blur our image, which I've tried. So I've taken this image and I've used our 33 by 33 element convolution matrix that was used that used Pascal's triangle 32 row to generate all its values, and then the values were normalized, and this is the result. That's the blurred image. So it's very quick and simple to use a non-recursive Pascal's triangle implementation to generate all the values you need for a convolution matrix to blur an image.